Maybe you've seen this. If you watch football, you've probably seen it. If you don't watch football, you probably haven't. I like this. View. Okay, let's go to, let's stop this. Okay, let me go to View. Full screen is what I'd like. Okay. Let's see. Let's go back here. Let's see how this plays. There's a Jeep, a car, going through. Oh, what's that in the sky? Look at that. Whoa! Gives you some idea what a meteor is like. That meteor, by the way, the movie is not real. It's actually an ad for Toyota. Their car is meteor-proof, right? And what I like about it is it gives you some sense. This meteor is probably no bigger than this meteor. Whoops. Shouldn't put the meteor in the same pocket as my iPod. Okay? Here's a little meteor. This meteor is probably about the same size. Okay, but imagine this thing, except made out of TNT. Now, a meteor coming in at full speed, not slowed down by the atmosphere, will have something like 100, 150 times as much energy as if this were made out of TNT. Okay? So imagine explosive like this and what it would do. Now, this meteor would have a lot more energy than that, so maybe the meteor was smaller than this. But let's watch it again coming in. It's just sort of a neat movie. View, full screen. Here it comes. There's the truck. This is the ad for the truck. Ad for that truck. Anyway, what's that coming in? Oh, look at that. Whoa! Okay, so why did it explode? Explode because it had so much kinetic energy, energy of motion. What is kinetic energy? Well, energy is energy, but sometimes you compress a spring and it has that energy in it. Energy of the force. Force between the particles. That energy can be released from the spring. I get energy when I eat food. Sometimes it's called food energy. You know, they give different names to it. Food energy, kinetic energy, potential energy. Those names, it's all energy. It's all in calories, or if you like, joules. There's 4,200 joules per calorie. A joule is a scientific unit. But energy is energy. And if I wish to jump up, I take some of the there's energy in my muscles, then I release it, and it becomes kinetic energy. Now, the kinetic energy goes to stretch the spring between me and the earth. We call that the gravitational, basically the gravitational binding of me to the earth. That's energy? If I lift this up, it takes energy to lift it up. Why? Because the earth is trying to pull it down. The modern way of looking at this is that in between the earth and the meteor, there is a spring. You can't see it. You can't feel it. The spring actually, according to quantum theory, consists of a large number of particles zipping back and forth here. So it's like a rubber band. These particles are called gravitons. And we'll be talking more about quantum theory as the entire semester goes. But in understanding the gravitational energy, just think that you're stretching that band of gravitons. And it's trying to pull it back. And I won't do it quite so high. It does. When it pulls it back, the energy that was in those gravitons goes into speeding this thing up, giving it kinetic energy. The kinetic energy is also measured in calories or in joules. If you use the physics formula, you say the energy is equal to 1/2 mv squared. And you measure this in kilograms. A kilogram is about 2 pounds. Okay, and you measure the velocity in meters per second. So there's a meter, and there's a second. So if you go 1 meter in 1 second, that's how fast you're going. I'm not going to ask you to ever plug into this equation. That's not what this class is about. But some of you want to do a little bit more than what this class is about. And so I'm giving you this range of things, but I'll tell you when it's not required. So you plug into this equation and you put in a meteor. Put in a meteor. There's a kilogram meteor. I don't know, half a kilogram, something like that. And you have it going at a typical speed. Now, what's the typical speed for a meteor? It's about 30,000, or about 30 kilometers per second. 30 kilometers per second. That seems awfully fast. A kilometer. That's less than a mile. So it's about 20 miles per second. 20 miles per second. That's like San Francisco to here in about 2/3 of a second. That's pretty fast. That's how fast this meteor was coming in. I don't know if they did it right, but this gives you this. What I like about this movie is it really gives you the impression that things are coming in fast, which it is. By the way, I showed that. I was in the midst of trying to make some announcements here, and I decided to jump ahead. So now let me make my announcements by unplugging this and seeing if I can plug into here. This is a very modern setup we have here, but they still didn't anticipate the fact that someday we might actually use personal computers to supplement the class. Is that going in there? Little side on the downside? No, that's a male. I guess I have to plug it in. Just turn it on. Okay.
It's here. Main.
Mm-hmm.
And that toggles it between the computer and that.
Oh, excellent. So they did anticipate it. So I was wrong. So there have been 2 GSI changes. This has to do with the fact that some sections are fuller than others. So the Monday section that you went to yesterday that was taught by Jenny is now taught by Paul. And the 109 that was taught by Paul is taught by Jenny. The one that Jenny is teaching is in Valley Life Sciences building. Some of you will find that more convenient, and some of you may just want to stick with Jenny because you just thought she was great. Paul is switching too. If you wish to switch sections, let me tell you how we're going to do it. Telebears, as you know, is virtually impossible to get anything done. So let's ignore telebears. The section you're in is really the GSI you're associated with. So if you want to switch sections, send an email to Sean, our head GSI. You all got email saying this. Send an email to Sean, our head GSI, saying what section you'd like to leave, what section you'd like to go to. He's going to collect these. So he's going to be the marketplace. And then he's going to try to make adjustments so you get into the section you want. May not happen right away. So if you want to make a change, but right now these are your sections, send your homework tonight to the right GSI. By the way, many of you have not quite figured out this procedure of putting in the right header. You may not know what a header is. Okay, sometimes it's called the subject of the GSI. What we do with 450 students and not enough GSIs, what we do is we have automatic sorting of the mail. So you go to the website and use the right subject. If you're doing homework, it has a certain layout that we want. In fact, what we want you to have is your last name, your first name, and the date homework is due, and send that to your GSI. If you have to miss lecture and are afraid you might miss a quiz, then send email to me. But please use the right header. It's a different header than this. Okay? So look on the website and try to get those things straight, because it's the only way we, understaffed as we are, thanks to the explosive growth of this class, can handle all this. So we're talking about kinetic energy, and I want you to think of energy is energy. This V squared means if you're going twice as fast in your automobile, you have 4 times the energy. If you go 50 miles an hour instead of 25, you have 4 times the energy. That means when you crash, that energy all has to go into ripping apart bones and flesh and crushing automobiles. 4 times the energy that you have to get rid of because you're no longer moving. Where does it go? It goes into, nice things like crushing bones. So think of that as you drive faster. It's 4 times the energy, that's the V squared. Suppose you go really fast. Suppose you go 100 times faster. Then it's 100 times 100. That's 10,000 times the energy. Now we're getting really, really big. Suppose you're going the speed of sound. speed of sound is, well, what is it? It's about, maybe when you were kids and you were afraid of thunder and lightning, your parents said to you, oh, thunder, that's just a noise. And the lightning, you want to know how far away that is? Just count seconds. 1,001. You see the flash of lightning. It turns out the flash of lightning took some time to get to you. You'll see the answer is it takes several millionths of a second. So that you don't notice that. Okay. Then comes the sound. The sound goes slowly. If you've ever been to a ballpark and you watch the batter and he swings the bat and he hits the ball and the ball goes flying and then you hear crack, because it took a while for the sound to get to you. You measure that time delay from when you saw it hit, you can measure the speed of sound. Speed of sound is one of the favorite things ancient scientists loved to measure. It was, it's slow enough. The number that I was taught by my parents is that for every 5 seconds, the lightning was a mile away. Okay, so I still do this. I mean, I see a flash of lightning, and I automatically start going 1,001, 1,002, 1,003, 1,004, 1,005, boom! Okay, so it was a mile away. You see the flash, boom! It was right on top of you. So, a mile per 5 seconds. I want you to know that number. Many of you knew it already because you had parents who taught it to you when you were 3. You didn't know what a mile was, but when you're 3, a mile seems like forever. These days, many of you run a mile, and some of you in under 4 minutes, so it's not such a big thing. But anyway, mile for a little kid is really big. So velocity of sound is 1 mile per 5 seconds. Now, a mile is about 5,000 feet, 5,280. So it's about 1,000 feet per second. Okay, a football field, well, this is 330 meters per second. That's how fast sound goes. That's like 3 football fields in 1 second. That's why if you see the baseball bat swing, it's only about 1/3 of a second if you're 1 football field away that you will hear the sound delayed. It's really noticeable. Another place you might do it is you're watching someone chop wood out in the woods, and you see the axe come down. Chomp! Chomp. The one place where this is completely violated, of course, is in the movies. And to me, movies would be so much more realistic if they put in this delay. In movies, the lightning and thunder always occur at the same time. It loses some sense of reality in me because I'm so used to the thunder coming late. You see a flash, and then you have this period of anxiety. How soon is it coming? Not too soon, please. Or you see a battle scene, and there off in the distance are the ships going boom as they fire their cannons. You hear the boom right away. In reality, it's not that way. Now, we talked about gravity and different kinds of gravity. This is a demo that always makes me a little bit nervous. I'm not quite sure. In fact, the guy was supposed to give me some instructions on how to set this up, and he left. Doesn't even seem to fit. The idea here is I'm supposed to, when I release this ball, what happens is it's a little bit further from the Earth. So as I release it, it's getting closer to the Earth. Anyway, watch me directly. It's more fun. And it gets closer to the Earth, so the gravitons are compressing. It's picking up kinetic energy. Interesting thing. At the bottom of its swing, it's moving exactly the same speed that it would if it fell that far. You see, because the energy is going from gravitational, sometimes called potential energy. These are just names. It's going from the gravitation of the gravitons. If it fell straight down, it would pick up exactly the same speed, except this speed is it's going that way and not that way. Then as it swings over to the other side, if it doesn't hit anything, it will lose its kinetic energy, its motion energy. It'll slow down, and over here it should come to exactly the same height. That's one example of conservation of energy. And then As it slows down, now the gravity accelerates it back. And it comes down, should pick about the same speed when it's here, and then it should come back to the same place. Now there's some energy being lost because it's pushing air out of the way, but just imagine the weight of the air compared to the weight of this. This has so much energy that even though it loses a little bit of energy, if it were a feather, it wouldn't make it across the room. Because the feather weighs not much more than the air. But this thing, because it weighs more, so it should come back and just to the same place. We'll see. I'm supposed to stand here, and if I'm really sure of myself, let this thing sort of settle down. It goes like that, and it should come straight back. This bar will protect me, right? That's not much of a swing. Next time we'll have to do it from a ladder. It's not very impressive. I can't see it now. The bar's in the way. Whoa! Okay. Anyway, conservation of energy. Whoa! It's a bowling ball. You tell that it has some holes in it. Okay. So, homework tonight, talk to Sean, email Sean. We're setting up office hours for the GSIs. We're talking about speeds, and the speed of sound is 330 meters per second. Now, this is the amount of energy. Okay? Now, we can calculate the number of joules when something's moving. We can compare that to dynamite. And on this old chart that we were looking at, I've done that. Here we have an asteroid or a meteor moving at 30 kilometers per second has 165 times as much energy as the same weight of TNT. And about 15 times more energy than an equal amount of gasoline. Now, what happens when the energy is lost? I mean, here we have energy. Where did it go? Turns out that where it went is this thing in the table got a little bit hotter. Just a tiny little bit. What do I mean by hotter? Hotter and what it means is actually one of the oldest mysteries of physics that was finally solved and really understood in the late 1800s, early 1900s. In fact, Einstein played a major role in the understanding of what it means to be hotter. If you think about it, it's really mysterious. We think about what is temperature. We all know what temperature is, right? Or at least we think we do. But what is it really? What does it mean when you're hot or cold? Well, you're hot. Try to turn that into physical sense. People struggled with that. When you're hot, do you have something more in you? It turns out the answer is yes. The answer is what you have in you is more energy. Heat, it turns out, is energy. Well, what kind of energy? It's kinetic energy. It's moving energy. That's what heat is. It's moving energy. Let me give a demonstration. Let's see. Can you lower that screen down here just enough to see this? Does that screen come down? Oh, I lower this one myself. Okay. Think of these things as atoms. Now, what is an atom? An atom is, well, there are approximately 92 different atoms. The reason I say approximately is that some of the atoms that are listed up there basically don't exist unless you make them. They're naturally radioactive. If I can find my pointer hidden in my secret pocket deep in my hidden cargo pants. You see technetium. It's in funny letters. It's because you really don't find it in nature. It's radioactive, and it's all disappeared. So when I say there are about 92 elements, there's actually plutonium, which is, it all fits into this one square called the actinides. There are all of these elements there. And there's plutonium. And you think you don't find it in nature, but it turns out you do find it in nature because there's a little bit made from natural processes. It's very, very small amounts. So there are approximately 92 of these things. Each one consists of a nucleus and electrons going around that nucleus. So For example, a hydrogen atom has a heavy particle called a proton and a light particle called an electron that's in orbit around it. Just which kind of orbit is something that we didn't understand until, 1925 or so. Just how that electron orbits, and that's really the subject of quantum mechanics. But most of the weight, more than 99.9% of the weight, is in this proton. The electron takes up most of the space. So this thing here is typically several angstroms in size. Angstrom. I'm not even asking you to know the word angstrom. It's about 10 to the minus 10th meters. And this atom may be 2 or 3 times 10 to the minus 10th meters in size. That seems pretty small. If you look in a microscope, you can magnify things, but an ordinary microscope can't let you see an atom. The atoms are too small. A microscope, the smallest thing you can see, and this I do want you to know, the smallest thing you can see is called 1 micron. You can see why it's called a microscope. Micro meaning small. 1 micron. 1 micron is a millionth of a meter. 10 to the minus 6 meters. Millionth of a meter. Sounds pretty small. Except a red blood cell, you've seen pictures of red blood cells. Many of you have seen them under a microscope. That's about 8 microns. So a little bacteria, some of them are less than a micron, some are larger than a micron. A micron is getting down to a realm which is really interesting in biology these days. You look at a micron, you look at the nucleus of a cell, you look at things that are going down inside of the cell, and you find there are structures on the size of a micron. But to understand the molecular structure, you have to get down to the atoms, and you can see there are about 10 to the minus 6 versus 10 to the minus 10. So that's 10 to the 4th. That's 10,000 times smaller. So think of a red blood cell. And there are only 10,000 atoms across it. Seems like a lot. I think 10,000 isn't that big a number. I mean, a centimeter, 100 centimeters is 100 centimeters. I mean, a meter is 100 centimeters. 100 meters is 10 to the 4th centimeters. So 10 to the 4th isn't that big a number. It's the number of centimeters in a football field. Yeah, it's a big number, but hey, you could actually imagine counting them. When you were a kid, you might have wanted to count up to 1,000. Some kids count up to 10,000. You could do it. So when we're talking about a red blood cell, or something a little bit smaller, we're talking about that many things across it. So it's not really tiny infinitesimal. It's just too small to see with a light microscope. We can see atoms with more advanced kinds of microscopes, which we'll be talking about in this course. Electron microscope, you can actually see individual atoms. So that's what the atoms are. When the atoms combine together, they form molecules. So water, for example, it's called H2O, consists of 2 atoms of hydrogen and 1 atom of oxygen. Oxygen is up there in the upper right. It's colored red on this plot. And I misplaced my laser again, so I can't point to it. Ah, there comes my liquid nitrogen. Okay. Somewhere here I have my laser. I will find it. Now, I want you to imagine that these little balls here, that we're using some sort of advanced microscope, and we have those here's my laser. So there is oxygen right there. There are only 92 of these things. Chemists and some physicists get to know these things. It's sort of like getting to know, I don't know, your team or something. You spend some time with them, and pretty soon it doesn't seem like such a big number. Or maybe your fraternity. So each one begins to have a personality. My friend Frank Asaro, who's a chemist, has a deep experience with iridium and osmium and rhenium and tungsten and tantalum. He knows these things, better than I think he knows me. I know some of them. I know hydrogen pretty well. Carbon is really important. Neon, helium. I know some of these things, but it's more of a casual relationship. Anyway, there aren't that many of them. And I don't expect you to learn them all. But it's good to know that there aren't that many of them. And therefore, if you wanted to really study this stuff, pretty soon you'd know them all. And then you start wondering about what's inside of them. And you learn there's not much inside. They're all made out of protons, neutrons, and electrons. So you think there's something more simple, more elementary than the atoms. There are 92 atoms, but hey, there are only 3 of these things. Well, it turns out there are some other little things in here, but It's not too complicated. Basically, all these things are made out of protons, neutrons, and electrons. Each one here, this one has 1 proton in the middle. This has 2 protons in the middle. This has 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You catch the pattern. That little number up there called the atomic number is the number of protons in the center. In fact, because the protons attract electrons, there's the same number of electrons in each atom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the atoms are relatively simple, but when they form together, they create molecules. And in the air, the kind of molecules we have, about 80% of them are 2 nitrogen molecules, 2 nitrogen atoms forming a molecule. There's nitrogen. About 19-20% is O2. It's about 1% neon. Argon. That's the atmosphere. It's a little bit of water vapor. The little bit of water vapor is what we call humidity. So there's a little bit of water vapor mixed in, but it's much less than these are. And when you cool things out, the water vapor tends to form droplets. We call that rain. So here we have these things. These atoms and molecules. In this case, they would be mostly molecules. Molecule simply means more than one atom, so nitrogen is a molecule, oxygen is a molecule. This is an atom, and it's also the molecule of argon is just one atom. But that's not the way they really are. Not in the air. They're moving. This turns out to be the key to understanding temperature and heat. It's that these things are in motion. And the rules turn out to be far simpler than anybody imagined. They had all sorts of complicated ways of trying to understand what is temperature. They thought maybe it's a liquid. It's a hidden, mysterious liquid that gets into things. When this thing gets in, it's hot. When they call it, had names for it, phlogiston and things like this. They made up all sorts of bad theories. Keep that in mind today as you read about new theories. That the theory of temperature took a long time to work out, and most of the theories published were wrong. When you read about some new theory that's being published, odds are 90% it's going to turn out to be wrong. It's the way science goes. We do experiments that can prove some theories right and some theories wrong. The theory of heat was one of the great mysteries for a long time. There are all sorts of strange things about heat. I don't know if you've ever picked up a glass of water, and you pick it up and say, wait, that's not glass, that's plastic. You know as soon as you touch it. So how do you know? If you start thinking about it, you learn by experience. You learn this thing, oh, that's glass, it doesn't break. Boom. Oh, that's glass, it does break. Yeah. Okay, so these things, how do you tell? The way I tell is by how it feels in temperature. A glass feels cooler. Try this. Find a window somewhere. The blackboard is a good example. You feel that. Oh, it's cool. And then you feel the wall. Well, that's cool too. The wood. No, that's not cool. Odd. So is everything a different temperature? Huh. Zeroth law of thermodynamics states, but this doesn't mean that I have explained why it works. The fact is, there are more mysteries about this than most physics classes would let on. But the zeroth law of thermodynamics is that you put things in a room together and you have no energy coming in and no going out, and they're just sort of sitting together, and you just wait. And if you do that, everything reaches the same temperature. It's called the zeroth law of thermodynamics. It's rather mysterious. I haven't even told you what temperature is yet. For a long time, nobody knew. Temperature was what you measured with thermometers. You know, you put a little bit of liquid in a glass tube, and when it gets warm, it expands. And by seeing how much it expands, you can measure something they called temperature. But they didn't know what it was. Why? Why does this stuff expand when it gets warm? What does warm mean? And the zeroth law was really hard to discover because this table is cooler than this. They don't seem to be the same temperature. You hold a plastic glass and it seems warmer than a glass. What's going on here? Let me just tell you the answer on the glass and the temperature glass. See, we're not all at the same temperature in this room. The room is somewhere around 65 degrees, 68 degrees Fahrenheit. And I am closer to 98.6. So you see, I'm not at the same temperature in this room. I am warmer. If I were 65 degrees, I'd be dead. So I'm warmer. So when I feel a piece of glass or a piece of metal, ooh, this feels cold. Well, there's liquid nitrogen, okay. When I feel the blackboard, what I'm sensing is my body, which is warm, losing heat. It's traveling into the blackboard. So it feels cool to me because my skin is cooling off because it's losing heat into the blackboard. So I don't really sense temperature. That's why it's so confusing. I don't feel the temperature of that. What I feel is that I am warmer than it is, and therefore I start to cool my skin when I touch it. With wood, it turns out wood is the same temperature as the room, the same temperature as the blackboard, but heat doesn't flow very easily into wood. And therefore it doesn't cool my hand. So what I'm really sensing is the flow of heat, which is called conduction. Okay? Now, I still haven't told you what temperature is. I'm talking about these things, I hope to give you a little bit sense of the mystery of this thing, so that you'll appreciate the amazingly simple answer when I finally tell you. I might as well finally tell you. It turns out that temperature is the hidden kinetic energy of the atoms. You take a solid, and they're usually not sitting here like this. They're not sitting there all stationary. They're joggling a little bit. Let's see if I can make them joggle a little bit. Maybe I have to turn this thing on. There. See how they're joggling a little bit? It turns out that what we call temperature is that. This has energy. It's hidden because you don't see it. It's hidden because the molecules aren't moving. The molecules in this wood are joggling, but they don't go anywhere. They stay in that place. And so they're shaking. If I cool it down, they're shaking less. Put it in the refrigerator, and the shaking goes down. So that's the secret to what heat is. And what is temperature? What's the difference between heat and temperature? Well, let me add more kinetic energy. You're going to see this thing turn into a gas. So let me add some more kinetic energy. That's sort of like a liquid. Kind of noisy, isn't it? Okay, so when the jostling gets so big that the particles can slip past each other, we call it a liquid. If you cool it down so they're jostling less, then you no longer have a liquid, you have a solid. That's called freezing. Now, I still haven't told you what temperature is, but when you get to, let's say, 0 degrees Celsius, 32 Fahrenheit, that's called the freezing point of water. It's also the melting point of water. When you take liquid water and cool it to that point, the molecules can no longer slip past each other and we get a solid. If you get it above that point, it doesn't matter whether you're melting it or freezing it, the temperature is the same. Now, what happens as you begin to melt the ice, what you have is some of the things on the surface turn into a liquid. And then the rest of the ice begins to warm up. Eventually, it all turns into a liquid. But it takes time to do that. So it takes a while for ice to melt. You put some ice cubes in a glass of water, it may take 20 minutes for all the ice cubes to melt. In the meantime, the temperature stays at the melting point, the freezing point, which is 32 Fahrenheit, 0 Celsius. It stays at that temperature because any energy that goes into melting the ice. So it's a nice way to keep the temperature constant. That's why we use ice, to keep the temperature constant. But this is what melting is. Melting is when they slip, when they finally get so fast that they can overcome gravity and go off into space, we call that a gas. So right now, the molecules in this room are bouncing around. They are actually, well, I haven't said what temperature is yet. Here's the answer to what temperature is. This is one of the great discoveries in physics, and it's amazingly simple. We define the Kelvin temperature, the absolute temperature, and I never remember the number. So I don't want you to either. Well, you can, but then you can say you know something I don't know. Okay, and here it is. The kinetic energy of the molecule is equal to a constant, which is 2 times 10 minus 23rd. That's a number I don't remember, times the absolute temperature. Temperature is just the energy per molecule. That's all it is. The molecules are moving. Each one has a typical average kinetic energy from its motion. If you know that kinetic energy, you know the temperature. This is the relationship between the kinetic energy and the temperature. This is the equation you don't even have to write down. I do want you to know that temperature represents the hidden kinetic energy, the kinetic energy that's hidden, because the thing never goes very far. It just bounces back and forth. How fast does it move? This is a really interesting and critical number. How fast are the molecules here shaking? Well, they're not going anywhere. Yeah, but they're going back and forth. So they're instantaneous velocity. Well, some of them will stop for a moment and get going. You look at these things, some of them are moving faster than others. I'm talking about the average velocity. The average speed of these molecules. What is it in the air, for example? How fast are these molecules moving? I guess I lost it. Look at that. Slow. Anyway, the speed of molecules in the air, not by coincidence, is about a mile every 5 seconds. That's the number I mentioned earlier. That's the speed of sound. That's how fast they're moving. I want you to always remember that. The typical velocity at room temperature is about the speed of sound, and that is not a coincidence. When we talk to waves, we'll talk more about this. But when you make a sound wave, what you're doing is you're compressing it a little bit. You compress a little bit of air, and then it pushes on the air next to it. But it doesn't push on it until that air molecule gets over there. It's moving at about a certain speed. That is, these molecules are not going to put a force on the next one until they reach it. And so the speed at which sound goes is about the same as the speed at which the molecules go. So I want you to always remember a typical speed of a molecule is equal to the speed of sound, which is 5 miles every second, because that's what your parents told you about not being afraid of lightning. That's about 1,000 feet per second, because there are 5,000 feet in a mile. It's about 330 meters per second. That's about 1 meter every 330th of a second. About 3 milliseconds. I'm not going to ask you to do all these numbers, but I want you to basically know that the speed of sound is about a mile every 5 seconds, 1,000 feet per second, and that's the speed of the molecules of the air. And it's not a coincidence. We'll talk more about waves. We'll talk more about exactly how that works. But for right now, the sound can't go any faster than the speed at which the molecules move. Now, it's not true in a solid. In a solid, the molecules are already touching each other. And you push on this one, it pushes on the other one immediately. It doesn't have to move over there to touch it. So for a solid, the speed of a compression can go a lot faster. And it does. Speed of sound in steel, in granite, in the earth is faster than in the air. But in the air, it's set by that speed. Now, here's the really surprising thing about this. If you look in this thing, and I'll make this noise again, you'll see there are two different sized balls. Some big ones and some small ones. It's kind of hard to tell. There's not a big difference. Maybe I should put in some even bigger ones. What you might be able to sense if you watch this for, a few hours, is that can actually be mesmerizing, is that the big balls aren't moving as fast on average. Sometimes they get a big kick and they go flying. But on average, they're kind of slow. And the little ones are moving faster. Keeping that in mind, watch it again. reason is they're all at the same temperature. And that means they have the same kinetic energy. But kinetic energy is 1/2 mv squared. If they all have the same kinetic energy, then things that have big M must have small v's. So a big thing moving slowly has the same kinetic energy as a small thing moving fast. So this is a key thing. This definition of temperature is based on the physics fact that you put things in a box and they all start sharing energy. They don't share velocities. They don't all have the same velocities. They all get the same average energies, the same energies of motion. When they're in the room, if this thing is hotter than the air, then these molecules are moving faster. When they move faster and the air molecules bang into them, they tend to give up some of their energy to the air. And so they'll keep on giving up energy until they're moving at about the same, turns out not the same velocity, it's the same kinetic energy. Why is that? Well, if you have a big massive thing and it's something that's light, the light thing will bounce off faster than will a heavy thing. If this isn't obvious, think of a baseball bat. The baseball goes faster than the bat. You hit it with the whole weight of your body. Well, that's the way Ty Cobb used to hit it. You hit it with the whole weight of your body, get that behind it, and the ball will get more energy. Something bouncing off a massive object will pick up more velocity than something that's light. But the amazing thing is they tend to have the same kinetic energy. Now, if you think about some of the, this has all sorts of interesting implications. Let me give an example. When the universe was made, we believe the Earth, like Jupiter, had a large amount of hydrogen in the atmosphere. The big planets have lots of hydrogen in the atmosphere. We have essentially none. This is important for the hydrogen economy. We don't have hydrogen. The only hydrogen we have is the hydrogen that combined with oxygen and with other minerals like silicon to make water, silicon dioxides, rocks and stones and so on. We don't have free hydrogen. Why not? Well, it's because hydrogen is the lightest of the elements. Up there. Here's oxygen. H2 is 16 times lighter than O2. 16 times lighter. In the atmosphere, it will have about the same kinetic energy, but because it's lighter, it has to have a higher velocity. So if you put hydrogen into this room and just let that gas float around the room, it will reach the same temperature. That means the same kinetic energy as the oxygen. Same kinetic energy. It's a small molecule. It must be moving fast. It doesn't get the same speed. It's faster. So it turns out that hydrogen in the Earth's atmosphere picks up enough speed that it actually gets escape velocity. It launches itself into space. That's why we don't have hydrogen. Why does Jupiter have hydrogen? It has a much higher escape velocity. We haven't talked about escape velocity yet. We will next week. But if you want to leave the gravity, if you want to break away, what you have to do is to give an object more kinetic energy than the energy of the gravitons that are holding it in. If you give it more than that, it will go to infinity. It will get off. It will escape. It's called escape velocity. That's what we do when we're sending people to the moon. We give them escape velocity. So the hydrogen, because it's light, but has the same kinetic energy as the heavier things, must be moving faster. It gets escape velocity. It leaves, so we have no hydrogen in our atmosphere. Rather simple. Same thing turns out to be true for helium. The sun is 10% helium by weight. 10%. And yet, maybe it's 10% by number, actually. No, I think it's 10% by weight. And yet, it doesn't lose it because the gravity is so strong. But here on the Earth, we don't have helium in the atmosphere. The only helium that we get is helium that comes from the ground. And as we'll learn in a couple of weeks, the helium in your helium balloons all comes from radioactive decay of uranium and thorium in the ground. We'll cover this as the thorium and uranium emit helium when they undergo a radioactive explosion. And this stuff accumulates under the ground until we pull it out of the oil wells and put it in our toy balloons. We'll be coming to that. But when it gets into the atmosphere, it soon escapes because it's light enough that eventually it'll have escape velocity and it will get out. Let me give you some of the numbers here. This I call the absolute temperature. And it's the one that scientists like to use. There's another temperature we call Celsius. Celsius is equal to the absolute temperature minus 273. See, it's the same scale. Except for Celsius, they decided 0 would be when water freezes or melts. Whereas 0 for the Kelvin scale, this is called Kelvin or absolute. The Kelvin temperature reaches 0 when the molecules stop moving. So it turns out that in terms of equations and so on, the Kelvin scale works much better. When we talk about absolute 0, we don't mean 0 Celsius or 0 centigrade. 0 Celsius or 0 centigrade is where water freezes. We mean 0 Kelvin, which is C equals 0 minus 273. That's minus 273 centigrade. This is called absolute 0. Absolute 0 is when the molecules are no longer moving. Sometimes you'll hear people speculate about getting to a lower temperature than absolute 0. That means the molecules are moving slower than 0 velocity. So what does that mean? Well, it's nonsense. Someone will say, how do you know you can't get below absolute 0? Oh, well, how do you move slower than stationary? That's your answer. By the way, since there is no possibility of getting temperatures below absolute 0, some scientists decide, let's use negative temperatures in a different way. And so they come up with a new interpretation. And they will say, from now on, by temperature, I'm not going to mean the kinetic energy of the molecules. When it's negative, what I'm going to mean is the distribution of molecules in different energy levels. No, you don't have to know this. The reason I'm telling you this is every now and then you will see some scientists say, I got to a temperature of below absolute 0. And every physicist knows what they're referring to. They're referring to a different definition of temperature that is useful only when you get to negative temperatures. And in lasers, they'll talk about negative temperatures. But, physicists just can't let a whole realm of numbers be unused. But the standard definition of temperature is that it is the kinetic energy per molecule. And if you want it in Celsius, you've got to subtract 273. I'm sorry, add. If you want Celsius, you subtract 273. And that'll give you the Celsius temperature. Fahrenheit is very similar. Fahrenheit, the scale, and Fahrenheit was a great inventor of thermometers. And so he created this thing. He had to put a scale on it. So he decided that the coldest that he could get was when he mixed ice and salt. And he called that 0. Okay, we now, that's 0 Fahrenheit. 32 degrees below freezing. The warmest he could get was so hot it wasn't usable, so he took the human body temperature. And he said, that's going to be 100. Actually, the amusing thing is he did it the other way around. He had 0 as being the human body temperature, and he had 100 as being the temperature that you could get with ice. And so it was an upside-down temperature scale compared to modern standards. It doesn't really matter. It's just a thing on a Fahrenheit thermometer that you could read. And it eventually got changed. And now, we in the United States use Fahrenheit. Everybody else uses Celsius. If you want the Fahrenheit temperature, you take the Celsius temperature and you multiply it by 9/5. So you get bigger degrees, and then you subtract 32. Let's see, you add 32. If I want 0, then it's 32. So this is the equation. It's also based on 100. I mean, one isn't metric and the other unmetric. It's just that when Napoleon was deciding he wanted to change the world number system so everybody could be French, they came up with the Celsius system, which is 100 degrees between water freezing and water boiling. Whereas Fahrenheit had 100 degrees between ice and salt and the human body. They're both 100 degrees, just different definitions. Anyway, we're stuck with these two things, and I still know Fahrenheit much better than I know Celsius. It used to be called centigrade. Centigrade, because it's based on 100, say 100 degrees. Of course, Fahrenheit was also based on 100 degrees, but nobody remembered that. And then, again, the scientists doing this felt that it's terrible to have a number that's not honoring someone in their field, so they named this after Mr. Celsius. As near as I could tell, has no scientific achievements whatsoever, but he got his name honored in quite a way. Glenn Seaborg got his name. He was a professor here. He died a few years ago. One of these elements here is called seaborgium. It's over here somewhere. Oh, seaborgium, let's see. It would be, there it is, seaborgium, 106. By the way, you may wonder about some of these things. Glenn Seaborg actually discovered plutonium. Plutonium is here. He also discovered neptunium. He was naming them Uranus, Neptune, Pluto. He named them sort of after the planets that were then around. And then after that, they started discovering more and more and more. And they're all being discovered here at Berkeley. That's why the next one was called Californium. And what's this one? Berkeleyum, or Berkelium, or whatever. Berkeleyum, named after here. Okay, and, or maybe that's wait a minute. Which is, now I'm confused. CM. Curium, they named it after Curie. And then this one is Californium. And then Fermium, Mendelevium, Nobilium, Lawrencium, named after Lawrence, professor in this department. Boy, how many people do we have? We have Lawrence, we have Seaborg, okay. Named after, I can predict with confidence there will never be a malarium. Okay, I'm not in that business of finding new elements, and nobody would think of honoring me in that way. Okay, so this is the temperature scale, and converting between temperature scales is a pain in the neck, but you should know that freezing is 0 Celsius and 32 Fahrenheit. You should know that. It's just a matter of educated knowledge. Boiling of water is 212 in the Fahrenheit scale, and except when you're in high mountains. We'll talk about that soon. And it's 100 on the Celsius scale. And that absolute 0 means when the motion completely comes to a stop. Turns out it doesn't actually come to a complete stop because of quantum mechanics. There's always a little bit of residual motion, but at least classically it would come to absolute 0. Absolute 0 is when the motion stops. You're not going to get below absolute 0 for that reason. Now, take a look at this again. Okay, so let me turn this on. Let me heat it up a little bit. Notice how it pushes against that surface? That's what pressure is. Pressure is you are standing here and molecules are bouncing against you and they push on you. Now this hand has no pressure on it. It actually has pressure on both sides. Molecules are hitting it here and they're hitting it here. Hit it on both sides so it doesn't move. Well, sometimes they're going to be more hitting it on this side than that side, right? So actually it will move a little bit. But such a tiny amount that you don't notice it unless you're looking at pretty small particles. We may do that next time. I may set up something where you can actually see the thing jitter. This little jitter is characteristic of things that are at room temperature. Everything shakes a little bit. This little bit of shaking is responsible for all sorts of things. In a wire, there's a little bit of the electrons shaking. Because of that, you get an electron signal even when you're not tuned to a radio station. If you ever listen to a radio and you hear something that sounds like this, you're hearing the electrons shake. You're hearing the electrons move in and off the wire just because of the fact that they have some kinetic energy. Old TVs, you don't have to get to so much on the new ones, but the old TVs, if you were in between channels, you see a whole bunch of dots. And those dots were when you have no signal. So why are there dots? Why are they changing? The reason is these little, maybe we should get a demo of that, these little electrons sometimes jump off the wire and they give you a false picture of just noise. It's one of the challenges in electronic engineering is overcoming this kind of a noise. Just the fact that the electrons in a wire are moving means sometimes they move when there's no signal. And you don't know. You think that's a signal. It gives the hiss of the radio. It gives a signal on wires that becomes a fundamental limitation on how much information you can send over wires. Sometimes to get rid of this noise, what they do is they cool the wires. Now you understand why. You're not asleep, are you? Hello? Respond? You give him a tap? Yeah. Wake up. Respond. You just missed something. I'll repeat it. This is important. That even the electrons in a wire are shaking around. This gives you a signal, because signals are moving electrons, even when you haven't put any signal on the wire. And because of that, you will hear a hiss noise. And if you want to reduce the hiss, one of the ways of doing it is cooling the wire. And you can see why. You want to bring those electrons so that they're not shaking. They move only when you want them to move. They're not shaking like that. That's a kind of noise. The molecules in a room are moving around, and then they bounce off something like that. They produce a pressure. Let's say, I think air. This is something I can do. Right now, this thing is a can. You can see it's, kind of an old, beaten-up can. But anyway, it has molecules bouncing out about this. Why don't they crush it? It turns out that these bouncing molecules put a force on. If you want to keep something from moving, you notice when these bounce, it pushes this piston out. Now I can hold it in. Whoops. I can hold it in. But to hold it in, I have to put a force on it. Suppose we had the molecules in this room, and they were pushing against this can, and suppose there were no air molecules in the can. Then they would crush the can. If we want to hold it out, it takes about 15 pounds for every square inch. We call it the pressure of the air. It's the force you need to keep it from collapsing. If I had a pump, I could pump out the air in this and you'd see what would happen. Oh, I have a pump. Good. Let's pump the air out and see what happens. This must turn on somehow. I bet there's a switch on it. I'm sure there's a switch on it. Okay. The air pushed it in. Why does the air, if the air is moving, why doesn't it just escape? The answer is the weight of the air above it. If I heat up the air, then the pressure increases and the air spreads out. When the air spreads out, it doesn't weigh as much. What happens when something doesn't weigh as much? Let me heat up some air. Called the hot air effect. Let me see if I can. Let me get some gas on this thing. This goes here, here, here. Okay. There, so I'm making it hot. Why is it blue? We're going to be talking about that. It's blue because it's hot. Because it's hot, the electrons are shaking. Because the electrons are shaking, it turns out they emit electromagnetic waves. That's why it's blue. We'll be talking a lot more about that as we come to light and waves and shaking. But heat, when you heat up a tungsten filament, the reason it glows so bright is the electrons are shaking faster. When they're shaking faster, a shaking electron emits an electromagnetic wave. We'll talk more about that when we get to waves. Here I'm heating up this gas, and I'm going to put this thing right on top of it, and now I'm heating up the air. Now the air inside of this is getting warm. Because the air inside of this is getting warm, it's expanding. This is expanding. It doesn't weigh as much as the air out here. So this air weighs a certain amount. It's not very heavy. Over here the air is heavy. They come together down here. This heavy air has greater pressure than this light air. So result, this heavy air pushes the lighter air up this way. You do that here. Well, here, let's see. Here's a liquid. What I'm going to do is heat up the liquid. When I heat up the liquid, it will expand. When it expands, it will weigh less. And let me get this going. I'll turn this one on over here. Turn it down a little bit. Okay, that's going to heat up this liquid. So what's going to happen to this liquid? This liquid is getting hot. The molecules are bouncing faster. Because they're bouncing faster, they get pushed apart. It expands when it gets hot. Essentially, almost everything expands. There are a few exceptions, but almost everything expands when it gets hot. How much does it expand? Well, for every degree, it's about a part in 1,000. Some things are apart in 10,000. Some things are apart in 100. Some things are apart in 100,000. They're about a part in 1,000 or a part in 10,000. It's expanding a little bit. So this is expanding. That means this tube weighs less than this tube. Here, the weight of this is pushing against this. The weight of this is pushing. This one's pushing harder. Because it weighs more. The same amount of tube, but this thing is hot over here, and it's still cool over here. It's getting warm over there. It's getting cool over here. And as a result, this weighs more. And so because it weighs more, it pushes this out of the way. I think we can see that if we throw a little bit of color in here. We'll see what happens. And you see which way the water is flowing. Okay? So the water is now flowing in a circle because we're heating one side of it and making it lighter. In some sense, what we're doing is turning heat into motion. This is a kind of a motor. It's a very primitive motor, but it is a motor. That's what a motor is. A motor is when you get some sort of energy, typically in the form of heat, in a gasoline engine, which we'll talk about next week, or Thursday rather. With a gasoline engine, you create an explosion. You now have this hot gas. You want to turn that into the turning of the wheel of your automobile. This is a very simple one. Well, how about this thing here? We've been heating up. It's pretty hot in there. I cannot keep my hand there. So this air is rising now because it's being pushed down by the cool air over here. So this is a circulation pattern. This kind of circulation is extremely important. The same thing occurs in a thunderstorm. In a thunderstorm, sunlight comes down, heats one patch of land more than others because of their clouds. So this part gets hot. When it gets hot, the air above it gets hot. When the air above it gets hot, it doesn't weigh as much as the air over here, so it tends to go up. It gets pushed down by the heavier air. This heavier air they come together at the bottom. Like this, they come together at the bottom. But this side weighs less than that side, so this side pushes more because pressure is just the weight of the stuff above it. Pressure of the air is just the weight of the air above us. So, let's see. I think with a piece of plastic, I might be able to demonstrate that this air is flowing out of here. So let's see if it'll make this plastic fill up with warm air. Okay, so the plastic is now filling up with warm air. Oh, until it keep it away from the heat. So it fills up with warm air. The air inside of it, this is what a hot air balloon is. This is why you use hot air. The hot air weighs less, and therefore, at the very bottom, there's less of a force from its weight than from the surrounding air. So the surrounding air tends to move in underneath it. Now the air is still going up. Can you see it there? The air is still going up? No, you can't see it. But the air is still going up. It's just that this thing turned over. That's how a hot air balloon works. It works on the fact. Let's see. Am I turning off the wrong one here? There we go. So a hot air balloon works on the fact that the faster it is, which means the hotter, the greater is the pressure. When the pressure is, well, the pressure comes from two things. It comes from the weight. Here, the pressure is greater, so it tends to expand. And because it expands, it weighs less. Because it weighs less, it gets pushed out of the way from here. What happens in the air is the air pressure. Okay, let me. I think I may have confused you a little bit with the pressure. But let me just say that the air becomes less dense in here, the water becomes less dense in here, and as a result, we get this flow. This flow is called, it has a name, it's called convection. And it turns out convection is not only creates thunderstorms, this is like a thunderstorm. This is what causes the thunderheads to rise. It's the heating of the air below it. That's a thunderstorm. We also use it in our rooms. If you have a heater in the room, on one side of the room, what you'll find is the heat will tend to rise. That is, what happens is the heat heats up the local air. The local air expands, it weighs less, so it tends to rise like a hot air balloon. And then it'll stay up on the ceiling. And if you ever get up on a ladder or a chair, you say, boy, it's warm up here. That's because the hot air has risen. Now, if it keeps on going, then you may get a flow around in a circle, and some of that warm air will come down. But if you want a heater, you don't put it up at the ceiling because it'll just all the hot air will stay up there. You need, near the bottom, you want to get some convection going so the hot air eventually comes down again. But it's all based on that. We can do the opposite. Here we can take a liquid. This is liquid air. It's actually nitrogen. This is wonderful stuff. I love this stuff. It's liquid. It's well below 0 Celsius, and it's cold. And it can really hurt you if you stick your finger in it. And there it is. So this is nice. It's cold. It's boiling. It's boiling at room temperature. It turns out I can put my finger in it as well as I do just for a second. Okay, and the reason is when my finger goes in there, immediately it boils against my finger. It makes a layer of gas. That layer of gas doesn't conduct heat very well. So if I just do it for an instant, I can even pour this on myself, as long as I don't do it for very long. You'll notice when it's on the tabletop here, an interesting thing happens. It forms a little, look at that, shoot across. See it shoot across there? Okay. What's happening is the little bit of the liquid hits the table, warms up, makes a layer of gas, and then it floats on that layer of gas. Some people think that this is how firewalkers walk on hot coals. I've never tried it myself. But they say if you're a little bit sweaty and you walk on the hot coals, what happens is the sweat turns to gas, makes a thin layer of gas, and gas doesn't conduct heat very much. Why? Because it's 1,000 times fewer molecules per cubic centimeter. This is a number I want you to know. It could be on the quiz on Thursday, if there is a quiz on Thursday. Could be on the midterm. If you look on old midterms, you'll find it there. Gas is typically 1,000 times more spread out, 1,000 times less dense. Let's put some of this liquid nitrogen in here and use it to cool off this balloon. And let's see what happens as the air in this balloon begins to decrease. The air is cooling. And because it's cooling, the pressure is going down. Because the pressure is going down, it's being compressed by the force of the air on the outside. So you may notice it's actually getting a little bit smaller as the air inside cools. Eventually, the air inside may turn into a liquid. In that case, it'll be 1,000 times less dense. And that balloon is getting pretty small. So just as we can heat up air and make it expand and then it tends to rise, we can use this to make the pressure go down inside and eventually lose the volume. I want you to know that factor of 1,000 because it's really important in many things. That factor of 1,000, when dynamite explodes, what you're doing is turning the energy that's in the molecules, you're breaking up the molecules and turning it into a very hot gas. So you release a lot of energy. A hot compressed gas has a very high pressure. That very high pressure pushes things away. It makes an explosion. So there's our balloon, made nice and small. Let the air inside warm up. Oh, here's something we could do. Let's see. Let us... How do I do this without... What I want to do is to pour some of this in this cannon. So the gas in there is expanding. I put a cork on this. The air is coming out there now. If I close that, of course, I mean, this is correct. Using liquid nitrogen, hey, you can do the same thing with a Coca-Cola bottle, right? Just shake it a lot, and as the gas comes out of the liquid from being dissolved in the liquid, you make a little cannon. This is great stuff. I sometimes use it to remove warts because if you put it on a Q-tip, you can remove a wart that way. Now, let's talk about what happens. Suppose I have an object that's moving at the speed of sound. then it has as much energy in it, in motion, as it has in the random hidden energy. It's only twice as much. That's when a bullet, you can shoot a bullet at the speed of sound with a really moderate rifle. And when you do that, you're putting as much energy into this as at the speed of sound. What happens if that bullet stops suddenly and all that energy turns into heat? Well, I say that room temperature about 23 degrees centigrade is equal to 300 Kelvin. I want you to know this number. That's room temperature in absolute scale. And this formula gives it to you right there. You just add 273, okay? And maybe it's 27 centigrade. Okay, so room temperature is about 300 Kelvin. A bullet will have as much energy in its overall motion as in its random motion. They're roughly equal when it's going the speed of sound, because the speed of sound means every molecule is moving at the speed of sound, but now the whole thing is moving together at the speed of sound. If that thing stops, all the energy goes into random motion, and now you've doubled the energy. That means you'll double the temperature. So if you stop a bullet, you expect it, and all the energy goes into the bullet, you expect it to heat up from 300 Kelvin to 600 Kelvin. That's 300 centigrade. Imagine you're the space shuttle now. You are going 18.3 times the speed of sound. 18.3 times the velocity of sound. Your kinetic energy is 18.3 times squared times the energy of your object itself. The space shuttle, when it's moving at this speed, has much, much more energy in its motion than it has in its temperature. When it comes to the Earth, it has to stop, so it has to get rid of that energy. So how does it get rid of that energy? Well, by running into the air. If it runs into the air, isn't the space shuttle going to heat up? Well, you don't want that, or it'll be, let's say, 20 times 20, that's 400 times hotter than room temperature. 400 times hotter than 300 K. 300 K times 400 is 120000. That's 120,000 degrees. The sun is only 6,000. So if all the energy of the space shuttle goes into heating the space shuttle, you get something that's hot, that's hotter than the surface of the sun, 20 times hotter than the surface of the sun. Obviously, you don't want to do that. So they designed the space shuttle. It has to lose its energy. Could use retro rockets. Yeah, if you want to make the space shuttle 1,000 times bigger, you can carry the fuel to slow it down. You have to carry as much fuel as you use to speed it up. So what they do instead is they have a special design so when it hits the air, the energy goes into the air, not into the space shuttle. These tiles are designed to have very low conduction. Because you don't want the space shuttle to heat up to 120,000 degrees. So the tiles are designed to have very low conduction. The energy goes into the air instead, and that slows the thing down. Well, the tiles glow red hot, but the energy doesn't get inside. Unless there's a broken tile. And then the energy is so enormous that you understand what happened with the Columbia tragedy.